Okay, so that's the stage that we got to where we had that question. Hopefully you should have an answer that the 3.6 nanocoulombs is attracted with a force of 5.6 times 10 to the minus 3 newtons to the left. So you've got that you can actually calculate the forces between charges, but why is there a charge on this point, at this point? So for that, we need to think of something else, which is we have electric field. So a field exists around this charged object such that that second charge will experience a force at that point in the electric field. Electric field is the force per unit charge, and it's at that point. Because it's got a direction, then it's a vector, so you quite often hear it referred to as electric field vector. And so if you've got a charge Q in an electric field, it will tend to go in the direction of the field lines there, and it will experience a force of the charge times the electric field. So the electric field is the number of newtons per coulomb, the amount of force per unit charge, and that's where these units, newtons per coulomb, come from. So F is equal to QE. Now at this point, if you're doing this unit after the gravitation work, you're thinking, oh, this sounds very familiar. And it is. Gravitational field is the amount of force per unit mass put in a place in a gravitational field. Electric field, very similar idea, and that's why you've got that it is the amount of force per newton that you've got at that point. And so F equals QE is given on the formula sheets. So if you had an electron which was put in an electric field here, you can notice that the electron is because the arrows for the field are going in that direction, then the electron will go in that direction, and electron's got a charge 1.6 times 10 to the minus 19 coulombs, mass 9.1 times 10 to the minus 31. And if it's put in this electric field of strength 230 kilonewtons per coulomb in a cathode ray tube, you should be able to calculate the force acting on the electron and the resulting acceleration by consideration of the field. So pause that video at the moment, try and work that out, and then restart it once you've got a couple of answers there and see how you compare. Okay, so hopefully you've got your own answers. That's what you should be getting, something like that, 6.7 times 10 to the minus 19 newtons for the force and an acceleration of 4 times 10 to the minus 14. Now that seems an awful lot, and that should be meters per second per second. That's a typo on my part there. It seems an awful lot of acceleration. People say, oh, hang on, but that's bigger than the speed of light. For an acceleration, you can have an acceleration like that because it's something very light and it's not accelerating for anywhere near a second, so it won't achieve the speed of light. So you can have such high accelerations. The electric field is quite often set up between two parallel plates like we've got here, positive and negative. You can see that the electric field lines are running positive to negative. If the field lines are set up between two plates, you get a uniform field. And so you end up with just that the electric field is just the voltage divided by the distance in that case. And anywhere that you put an electric charge in there, it's going to experience the same force between those 2 points. You do sometimes see drawn end effects here where the field tends to bulge out there, but that would be a uniform electric field. In general, the rules for electric field lines is that they do go from positive to negative. Remember, they're not showing the directions of electrons like our current diagrams do in circuits, but they're showing what happens to positive charges. They always connect. Don't leave, if you're drawing these with them hanging in space, they always connect from either one conductor to another or from a conductor to infinity. Because they're always trying to get away from each other, they will never cross, and they should enter the charged surface at 90 degrees. Field lines will always end up with an earth point or infinity, which is got a potential of 0 volts if it doesn't go to a negative. And these radial lines coming from a single point charge, because they're all trying to get away from each other, are actually straight, and so you should be drawing them with a ruler. If they do join from positive to negative, you'll see they still try and keep away from each other, and so you'll end up with this bulging out here, and some would technically go all the way out to infinity and come back in the way there. The greater the concentration, the greater the charge density, there's more lines, but also there's a greater field strength if they're closer together. and it does change shape if you add other charges in. I'll be coming back to a game that you can play online to play around with different charges and different field line shapes. Generally, you'll be asked to calculate the field due to a point charge. So you've got a single, we say point charge because it may be a very small sphere, but at a distance r away from there, you can calculate the field due to that charge q. If you take the charge divided by 4 pi epsilon and over r squared, it doesn't take a lot of derivation to see that that actually comes from the original equation, f equals q1 q2 over 4 pi epsilon r squared. All we've done is just divide both sides by the test charge that we put here, small q. So again, that's permittivity free space. Again, that's given in the data table, and that distance from the charge, that would have to be in meters. Careful that often this is happening in quite small distances, so you're often given distances in millimeters. You have to change that. Similarly, the charge is often given in nanocoulombs, so you might have to change that as well. It does follow the inverse square law. So if you think about what this graph is going to look like, if you plot the electric field as you go away from the charge, you could have a think or pause the video just to see what that would look like in your own thoughts. Moving on, it is quite a deep inverse square. So the further you are away from the charge makes a big difference because it's 1 over r squared to the field that you experience as you go away from the charge. And that's for a point charge. Because electric fields are vectors, then they need to be added as vectors. So if you've got two positive fields or two positive forces, then they add together to give you a resultant. If you've got a test charge which is positive between a positive charge and a positive charge, then it's going to experience two forces, a force there due to that one and a force there due to that one, and you've got to work out where it would go. I'm just realizing that should be the other way around. And similarly, you've got two forces here. If you put the test charge out away from two charges, you've got a force of repulsion, positive from positive here, force of attraction towards the negative, and you'd have to add those two together as two sides of a vector triangle for it to make sense there. Okay, so you be prepared. If you get a question like this, quite often at advanced higher, that angle in there will be conveniently 90 degrees. So that gives you a 90-degree right angle triangle, and you've got two field vectors, which you calculate by the field equation, that one there, and second one there, and you can add those two together and get a resultant, or similarly as it's shown here with forces, but you've got a bit of vector addition to do with that. So that's all about force and field. You may want to just pause this at the moment and go and do the tutorial on force and field, or if you're willing for more, then we'll go on to electric potential and energy. So there's a force is tied in with field, but if the electric charges have energy, then that's tied in with the potential. So potential is the energy required to move that coulomb of charge, unit charge, from infinity to a point. And positive charges have a positive potential, negatives have negative potential. It's not a vector, and so you can add or subtract them just as positive and negative. That V is in this equation that you did it higher, W or EW equals QV for the electrical energy is equal to the charge times the potential. This is where we've got the whole idea in National 5 that potential difference and voltage in a circuit is tied up with the energy that each charge has. So the total energy depends on the charge and the potential, but here the potential is a point in space. So your potential varies as you go further away from R, and if it's a negative charge here, then it's a negative voltage reducing to 0. You'll notice it's a different shape. It's a perfect hyperbola here, and that's because the potential, just like gravitational potential, is the charge that's setting it up, big Q, divided by 4 pi epsilon naught, the same constant, but this time just divided by R. Not R squared, just by R, and so that's why it's a hyperbola shape there. Similar to the equation at gravitation. And So we've got these equipotential lines as well as the field lines. There's areas of equipotential. So this could be maybe a positive 4,000 volt equipotential, positive